Hello, welcome everyone. My name is Brett Peterson, the Director of Sales and Operations for North, Central, and South America. I want to thank you for joining us today. As a point of introduction, Isograph has been creating and improving engineering software for over 32 years. Our headquarters is in the UK, and we have an office here in beautiful Alpine, Utah. I'd like to introduce you to Joe Beland. He'll be conducting our presentation today. He's our lead technical support from North America. Joe's been with Isograph for over 16 years and worked with thousands of organizations helping their employees become conversant with our software tools. Now today, Joe will be giving a high-level overview of one of our software modules. Now if this training is useful today for you, or you would like to learn more, please contact us directly at bpeterson. Let me just put that information up here, contact information, bpeterson@isograph.com, or you can visit our website at isograph.com. And so today we'll be discussing our software tool that covers FMECA, FMEAs, FMEDAs, and what I'd like to do now is turn the time over to Joe Beland and let him share the presentation, and we'll go from there. Let me share the screen with you here, Joe.
Sure. Yeah. Let me just share my share the reliability workbench.
We appreciate everyone's patience, and it looks like the screen, you should be able to see your screen now. Sure. And I'll turn the time over to Joe. Thanks, Joe.
Okay. So I've shared the reliability workbench, and I have a simple example FMECA project that we'll go through in just a minute. But first, let me just explain what FMECA, FMEA, and FMEDA are. Again, they're three related analysis types. So if you're unfamiliar with the acronyms, FMECA is failure modes, effects, and criticality analysis. FMEA is failure modes and effects analysis, and FMEDA is failure modes, effects, and diagnostic analysis. I'll give an example of each one as we go through the software. We'll start with the FMECA. That's our sort of our baseline, our jumping off point to understand how this analysis type works. So the point of all three of them really is to examine not just the failures of a system, but the failure modes and their individual effects. In many other analysis types, we consider a component failure as an input to the system. With FMECA, we're not looking at just simply the failure, but how does it fail? So one component can have multiple failure modes, and the results on the system of those different failure modes can differ. So for example, one failure mode could be significantly worse than another one. And so that's really the point of the FMECA analysis, is it FMECA and FMEA and FMEDA, is that they look not just at the failure of the device, but the specific failure mode and its effect on the system. They're used in a lot of different industries where you want to know not only what's at risk of failing, but how is it at risk of influencing or causing a failure of the system. Aerospace, automotive are two of our biggest users and two of our biggest industries for using these analyses types. Okay, I'll start with a simple example for FMECA to show the general overview of how this type of analysis works. So this is kind of a very simple system. This is not something I typically see in real life. We're just using this as an example. It's a simple computer system, which consists of several different components: power supply, a CPU board, a memory unit, which contains a ROM board and a RAM board. Each one of those devices, one of those subsystems, is made up of components: capacitors, resistors, integrated circuits, etc. And each one of those individual components has different failure modes. By the way, this is an example of what's called a hardware FMECA. There's two styles. There's hardware and functional FMECAs. Hardware FMECAs would go down to individual components like this, listing the failure modes of those components. A functional FMEA or FMECA generally just looks at the systems or subsystems and what they're supposed to do, and it considers the loss of the function of that subsystem. Okay. So for a given component, say for instance this capacitor, it has 4 different failure modes: shorted electrical, change of value, open electrical, and other. Each one of these failure modes has effects on the next higher level in the hierarchy. That would be the effects on the power supply. So the shorted electrical has the effect of incorrect meter reading at the power supply level. So if I go up a level to the power supply, you can see that incorrect meter reading failure mode. That in turn has an effect at the next higher level, at the computer system level. So the immediate effect is negligible effect for small changes. So if I go one more time, you see the end effect, negligible effect for small changes. And that's where the final end effect on the system that would be caused by, going back down to the bottom, the shorted electrical failure mode would cause. Okay. So that's the part of the analysis. That's the main gist of all the FMEA style analyses. We're looking at the components, their failure modes, and what the effect of that particular failure mode would be. Now, for all of the different ones, we need a way of ranking these failure modes, all the different analysis types, FMEA, FMECA, and FMEDA. We need to rank the failure modes. What's the worst possible occurrence, or what are the worst failure modes that we need to investigate, that we need to design better, or we need to take actions to mitigate? So we need a way of determining which is the worst failure mode. And that's where the main difference in the different analysis types, FMECA, FMEA, and FMEDA. I'll start with the FMECA method. And this is a very quantitative way of ranking the component failure modes. So it starts with the block failure rate. So this block has a defined failure rate. And this would come from some failure data source, manufacturer data sheet, a parts library, a reliability prediction that we might have done in the, one of the other modules of Reliability Workbench. So we start with the failure rate for the component. Each failure mode is assigned an apportionment factor. So the shorted electrical has an apportionment, that alpha, of 50%. That means 50% of the time when the capacitor fails, it's due to this specific failure mode, the shorted electrical failure mode. Okay. The failure modes can then also optionally have a beta factor. The beta factor is the chance that given the failure mode has occurred, the effect will occur. Because there's always a chance there could be a redundancy or something like that, that a failure mode could occur but not produce the effect. If there's a redundant component in play. So that beta factor allows us to specify it's not 100%, or it's not a given that the effect occurs. In this particular case, we're not tracking that. In many cases, we'll ignore that beta factor. Okay, so we have the component failure rate and the failure mode apportionment, and that allows us to figure out the failure mode failure rate. From there, we can apply a severity to the end effects. So this negligible effect for small changes is a severity rank 4. This is coming from a particular standard. MIL standard 1629 defines a way of ranking severities, ranked 1 through 4, where 1 is catastrophic and 4 is the lowest minor of severity. And those severities are then assigned a weight based on how bad it is. Catastrophic has a weight of 100. Minor is a weight of 1. So we take all that together, the failure mode apportionment, the component failure rate, also the component's operating time is another factor that comes into play, and then the severity. And what we can then quantify is what's called the criticality and also the risk of each failure mode. So I get 2 values for each failure mode, the criticality and the risk contribution. And this will help me figure out which is the worst failure mode in my system, which ones do I need to take actions around, which ones do I need to correct for. And we can even see that in a plot. There's a criticality matrix plot. Each red dot represents a different failure mode. Blue dots are the cumulative severity or the cumulative occurrence ranking for all the 4 different severity rankings. So it helps us figure out which are the worst possible failure modes. Okay, here's another graph showing the highest failure mode, shorted electrical, on failure mode 1.2.1. It's the highest failure rate failure mode. That would be back here, 1.2.1. This is my highest failure rates failure mode. Okay, so that's one way of getting at the criticality, or figuring out which is the worst failure mode and where we need to focus our attention for corrective actions. Before I move on and talk about the other methods, the FMEA and the FMEDA, let's take a quick example, a quick look at how to build the FMECA. It's actually really simple, really straightforward. If I wanted to build a new FMECA, I'm going to clear out this project, open a new project. Just suppose I'm starting from blank, starting from scratch, nothing created so far. I'll start by building either my hardware or my functional hierarchy by simply clicking the Add Block toolbar button right up here to add the blocks defining the systems, subsystems, components, functions within my FMECA hierarchy. So what does this represent? So if I'm going to build that computer system, this would be the power supply, right? And I could give it a failure rate. For higher level blocks, I don't need to give them a failure rate. That's inherited from the lower level blocks. So I can add that power supply, right? And then I added subcomponents. One of its components was that capacitor. So I can add a capacitor. And here's where I might enter its failure rate. So let's say it has a failure rate of 100 fits, 100 failures per billion hours. So that time unit represents. Okay. Now I can start adding failure modes for that capacitor. So one of those failure modes that we had was the shorted electrical failure mode. So I select the capacitor, click the red Add Failure Mode button, and I can add that shorted electrical. Okay, its apportionment was 50%. And we also want to define the effects of that failure mode. In in the example we had just looked at, the effect of it on the power supply was an incorrect meter reading. So I can add that immediate effect just by typing up here, incorrect meter reading. There we go. Select OK. Select OK again. It will add that failure mode. Change my grid view back to this one. It adds that failure mode. You'll see it up at the top here. I expand the failure mode in the top. It also shows the effect of it, incorrect meter reading, which then becomes a failure mode at the next higher level. It automatically creates that. If I go to that power supply, you'll see it automatically created that failure mode when I add it as an effect at the lower level. So I'd continue this process and flow this up through the hierarchy. Take this one. What's the effect of the incorrect meter reading? It was a negligible effect for small changes. Negligible effect for small changes. Select OK and OK, and now that's been created as an end effect for the system. I would then assign a severity. I don't have my severities defined since I created a new project. Severities are defined on a per project basis. I could easily create one. This is a severity rank 4, which is minor, the weight of 1. Okay. Now that's all I really need to run this analysis. Actually, I think it'll give me an error because I don't have all the failure modes yet defined for this. The apportionments don't sum to 100%. The program will give me an error message that says, hey, I don't think you finished here. You haven't finished defining the failure modes, and it can tell because the apportionments does not account for all of the failures of the capacitor. So I could then go through and add the rest of the failure modes for this capacitor. Now, obviously, that can be an arduous process, adding all of that and typing them all in. So there's ways of speeding up that process. One of them is via the apportionments library. The apportionments library allows me to predefine the failure modes for the common component types that I'm likely to see in my system. So what I can do is rather than manually creating the failure modes every single time I have a capacitor, I can predefine that and then essentially pull it from a library. So let me say I have a capacitor block. I can predefine its failure modes. That was an apportionment of 50. My change of value, apportionment of 40. My open electrical, had an apportionment of 5, as did my other failure mode. Okay. So I select to add that. Now, instead of having to, whenever I have a capacitor in my system, rather than having to manually add its failure modes, I can use the Add Apportioned Block choose that block from my apportionments library, and when I drop it in, it automatically has all its failure modes defined, predefined for me. And all I have to do is link them up with the effects. Okay. So that's an example of how to build the FMECA. It's a really simple and straightforward process. This can be sped up in a number of ways. We can import this block hierarchy. We can import the list of failure modes. It can be copied from one of the other modules within Reliability Workbench, such as the prediction module. There's other ways of speeding this up. We can also use the phrase library to save commonly used bits of text, so we don't have to do so much typing like I was just doing just now. So there's lots of different ways to speed up the analysis, so we don't have to manually build it one block by one. Okay.
So Joe, one quick question.
Sure.
If you could touch on possibly if a customer or a prospect might have content in, say, Excel or another format, is there a way to bring that in to the system?
Right. Yeah, absolutely. Yeah. So there's a couple different ways for FMECA. You can use the import feature, which can import from Excel, from Access, from a text file. And there's also another, in the special functions, another way, import free format FMEA. The main difference between those two methods is the format of the file that you're importing from, how the file is laid out. If you're using this one, the import file would have to sort of match the database of Reliability Workbench, which is simple enough to do. If you use the import free format FMEA, then you can have a file format that combines the hierarchy and the failure modes all into a single flat file.
Fantastic. Perfect. Thank you.
Okay, let me just talk quickly about the other two methods of failure modes and effects analysis. So FMECA was sort of our baseline, and that's a very highly quantitative style of examining failure modes and figuring out and ranking them, which is the worst risk failure mode. The other method that we might use would be FMEA, and for this I'm going to close out this file and go back to my example. And FMEA is a little bit more qualitative. This is good where we don't have that failure data. I'm going to swap over my standard. It's good where we don't have hard failure data for our blocks. You'll notice that we don't have to enter a failure rate or an operating time factor for any of the blocks. I generally see FMEAs used as a mainstay in aircraft analysis. You need to make sure you've listed out all your components and their failure rate, or excuse me, not their failure rates, their failure modes and their effects. So I've seen this used a lot in aerospace. Now, it's good in that we don't have to have really hard numbers for anything. Instead, the way we're ranking everything is basically on a scale of 1 to 10. Instead of entering a failure rate and an apportionment, which those numbers can be hard to come by, I enter 3 ranking numbers. They're the criticality ranking numbers, the severity ranking, the occurrence ranking, and the detectability ranking. Essentially what they tell me is the severity ranking is how bad is it if it does occur. The occurrence ranking is how often is it likely to occur. And the detectability ranking, or detection ranking, is how likely are we to find out about it. If it's a hidden failure mode, those are obviously a dangerous thing to have in your system, hidden lurking failure modes. So each one of these is ranked on a scale of 1 to 10. I open up the failure mode, you can see for each one there's a text descriptor. So is it a very remote occurrence, or is it a very high, very likely occurrence? Let's say this has low occurrence, and the detectability is moderately high. The severity, like the FMECA, is assigned from the end effect to which it contributes. So if this goes up to the negligible effect for small changes, if I assign that, say, a severity of 2, very minor, that will be inherited, propagated down to the bottom failure mode when I perform the analysis. Green traffic light, you see it inherited that severity of 2 from the end effect to which it contributed. And then the FMEA, the failure modes, are ranked by their RPN value, the risk priority number, the RPN, which is just simply the product of these 3 values, the 3 rankings. So that way we can rank the different failure modes. The ones with the high RPNs are more severe or are worst case failure modes, the ones that we want to maybe take mitigating actions or redesign around those failure modes. It's you can see this one's a little easier to do than a MIL 1629 style FMECA. It doesn't require the hard numbers, it's more estimates on these 1 to 10 estimates in these 3 ranked categories. The final style is, let me just open another project, the FMEDA. This is most commonly used in, say, automotive. There's two styles of FMEDA, ISO 26262, which is an automotive standard, and IEC 61508, which is a general process safety standard, an offshoot of 61508 to 61511, which is the most commonly used one, I think, which is that's oil and gas petrochemical process safety. So those are the two commonly used styles of FMEDA. So let's just take a look at the automotive FMEDA and how it works. The main difference with this one, from the 26262 standard, is that, if I open up the failure mode, we have a separate tab where we can set is the component safety related. If the failures are safety related, then we can set what percentage of faults are safe failure percent, what percentage of faults have the potential to violate the safety goal, if we have a safety mechanism in place, what percentage of faults are prevented by that safety mechanism, and then for those what are called multi-point faults, we have our detected and perceived percentages, so I can fill those out as well. And what this is used to determine in the automotive world is what they're really after two main things. One is single point fault metric, and the other is the latent fault metric. So they want to see not just the failure modes, but how many of those failure modes are single point faults, meaning there's no safety mechanism to prevent that failure from causing the hazard. And they also want to know, how many faults, what percentage of those faults persist through the system. So I'm going to enter values such as that. When I run the analysis, it will give me metrics overall, the result summary for my single point fault metric and my latent fault metric. Don't look too closely at the numbers for this example because I haven't finished filling out the values in this example. So don't look in detail at the numbers. I just mainly want to make you aware of what sort of calculations are done by the software when you're performing an FMEDA. Okay. Finally, the FMECA software, since it's part of the Reliability Workbench, integrates with all the other tools within the Reliability Workbench. As I sort of mentioned earlier, the prediction, you can grab those failure rates from the prediction. You can also use the data from the FMECA, say the failure mode hierarchy, in, say, an RBD or a fault tree. Going back to one of my other examples, we can actually create a fault tree from this FMECA project. So one of the downsides of FMECA is, as a systems analysis method, it tends to be a little simplistic. It doesn't have much in the way of redundancy calculation, aside from a simple value that we saw in the FMEDA, where you enter a percentage for percent caught by a safety mechanism. Aside from that, there isn't really a really strong, robust redundancy calculation tool. That's where we might step into the world of, say, fault tree analysis. Unfortunately, it's very easy to convert, to create a fault tree from the FMECA. There's an option to convert the FMECA hierarchy to a fault tree. It'll ask me for some confirmation, and then it automatically created a fault tree based off of the FMECA failure mode hierarchy. So we can see the failure modes for the individual components, failure modes at the next higher level, the power supply, and then the failure modes for the computer system. From here, we can take this and modify it, add redundancy, chop it up, move things around to more accurately model sophisticated logic within our system. Okay, any questions, Brett or Clint?
No, I think that's great. A great overview. I love how easy it is to integrate with all of our other software and modules. And I first just want to thank you for spending some time with us and sharing the overview, as well as, I appreciate everyone that's attended today for the presentation. One thing that I do want to mention is you can actually go to our website and obtain your own free demo. So let me show you here. Let me just add this just so you have the location here. So that's the website location, or you can even just go to isograph.com and go under products and availability workbench. Get a free demo, play around with our software, ask questions. If any questions come up, make sure to reach out to us. there's our contact information. But
Brett,
appreciate everyone's time.
I can't see
Yeah,
your screen.
go ahead.
Could you try resharing your screen? I can't see it.
Oh, I'm sorry. I thought I had that shared. Let's see here. Are you seeing that yet?
There, it just came up. Yeah.
Oh, perfect. Sorry about that. Yeah, I just wanted to let everyone know the contact information there for that free demo, as well as my contact information. Reach out. Let us be a resource. However we can help, we'd love to do so. Thanks so much, everyone, and have a great remainder of your day. Thanks, everyone.
Thank you.